In this problem, we are looking for key characteristics of a cardiac pacemaker circuit. We'll make use of the concepts of equivalent series capacitance, the fact that charge equals current times time, also the fact that the capacitor charge is capacitance times its voltage. Let's review the salient points from the problem statement. We have a cardiac pacemaker circuit that delivers pulses to the heart once every second. So here's our pacemaker, and it's connected across the heart. And let's go ahead and visualize these voltage pulses. Once every second, we have a approximately 5-volt pulse of only 1 millisecond duration. So these are pretty short pulses, but they occur once every second to establish the pacing of the heartbeat. The heart itself is modeled as a 500 ohm resistance, and the pacemaker is operated from a 2.5 volt battery. Now this pacemaker works in an interesting way. It charges two capacitors in parallel from this 2.5 volt battery, and there's some solid state switches that I'm not drawing here that would establish that connection. But then during the pulse phase, the solid state switches effectively connect the capacitors into a series, and that doubles the available voltage for the pulse. We then want to find the average battery current, so we can use that information to find the amp hour rating to achieve a 5-year battery life. Alright, let's see how we can think about the pulse delivery phase. The capacitors are in series. Each capacitor has the same value of capacitance, which is C. So we know that the equivalent of two series connected capacitors would be the sum of their reciprocals, and then we take the reciprocal of that. So the equivalent capacitance is actually 1/2 that value of capacitance C. Now this equivalent capacitance is charged effectively to 5 volts, because when they are stacked in series, that gives us 2.5 times 2 volts. Now the initial charge displacement as a result of the charging phase would be Q, which is the equivalent capacitance times that 5 volt value. Now the solid state switches only connect the 500 ohm resistance, which is our model for the heart, for 1 millisecond. During this 1 millisecond interval, we have a current flow I. Now the capacitor voltage will drop as energy is transferred to the resistor. The change in displaced charge can be written as Q equals the current times the time. That tells us how much charge actually moves from one plate of the capacitor to the other by way of the heart. So we can drop that in here and use that information that we want a drop of no more than 0.1 volt. That was part of this specification. We can then use that information to solve for that equivalent capacitance C sub EQ. And once we know that, then we've got the actual capacitor value that we're looking for. Now let's think about the average battery current. During the charging phase, the capacitors are disconnected from the heart and then reconnected back to the battery in parallel. We need to replenish the energy for each capacitor, and that will restore the original charge displacement. Now each capacitor needs a displacement of Q, so we have actually a total amount of charge that has to be separated of 2 times Q, and we are able to do this over 1 second, and that gives us the average current. Now in terms of the ampere hour rating, we would say on average the battery needs to deliver I sub bat times 5 years, which is 365 days per year, and multiplying that by 24 hours per day. Those units can't basically divide out, and we are left with amps times hours, and that becomes the rating that we're looking for. Now let's proceed with the detailed solution. Again, the heart is modeled as a 500 ohm resistor, and during the charging phase, the capacitors are connected in parallel to the 2.5 volt battery. During the discharging phase, they are connected in series and then connected across the model for the heart. Now these two series capacitors, connected as they are, have an equivalent capacitance of the sum of their reciprocals and then the reciprocal of that result. Now since the values are equal, we actually have the simple result that the equivalent capacitance is 1/2 of that capacitance C. Now during the discharge phase, we have a current that flows through the heart, which I will call I sub pulse. And we'd like to figure out the average pulse current, because we do know that the voltage droops from the initial value of 5 to 4.9 at the conclusion of the 1 millisecond pulse period. And again, that decline in voltage is because the capacitor is transferring energy to the heart. Now the average pulse current would be the average of the start point and the end point. So I'll sum those together and divide by 2. That's the average voltage, and then when divided by the resistor value of 500 ohms, that gives us an average current of 9.90 milliamps. Now the change in the charge displacement during this time interval, that is the time interval associated with the pulse, is 9.9 milliamps, which is coulombs per second. Then I'm multiplying that by time, in this case the pulse duration of 1 millisecond. So when we resolve the units there, we have 9.90 microcoulombs. Again, this is the change in the charge displacement associated with our charged capacitors. Now, how do we relate this back to capacitance? Well, we write that the charge Q is the capacitance, in this case C sub EQ, or the equivalent of the two series capacitors, times the capacitor voltage. Now that change in displacement is associated with a change in voltage. So that's why I'm inserting the deltas at that point. So the change in voltage during the 1 millisecond interval is 0.1 volts. Solving for the equivalent capacitance, we have 9.90 microcoulombs divided by 0.1 volts, and that gives us the value 99 microfarads. From that we can find the desired value of the actual capacitor itself, the individual capacitors, and that's 198 microfarads, meaning that we need a pair of 198 microfarad capacitors. Now, during the charging phase, we need to basically replenish the energy, which means that we have a change in charge for each capacitor. And each capacitor has to have 9.9 microcoulombs of charge displacement in the opposite direction. So that's the idea of injecting energy back into the capacitor. Now, this can take place over 1 second. Technically, that would be 1 second minus a millisecond, but I think we can approximate that as 1 second. So if we have coulombs divided by seconds, that gives us current. So it says that each current, or each capacitor, has an average current of 9.9 microamps. Therefore, the average current from the battery would be twice that. And this is one of the things that we were looking for in the problem statement. And our average battery current is 19.8 microamps. Now we're looking for a battery rating that can sustain this average current for a pretty long time, 5 years in fact. The idea is that we don't want to have to do a surgical procedure very often to be able to replace that battery. So we need 19.8 microamps times 5 years, and I resolve that into hours, taking the product of that entire number. We have 0.867 amp hours, and that's a rating of the energy capacity of the battery. Alright, let's recap what we did on this problem. First, we needed to find the equivalent capacitance of two equal valued series connected capacitors. We then determined the average current to the heart during the pulse phase, and then the total charge moved by the capacitor. We then calculated the capacitance based on the total voltage drop during the pulse, and then found the average current required to recharge the two capacitors. We then calculated the amp-hour battery rating from the average current required over 5 years.